Today we're reading a blog from Discord Engineering, How Discord Indexes Trillions of Messages. Back in 2017, we shared how we built a message search system to index billions of messages. So this is a blog post that they posted before this one, where they have described how they scaled their search system to billions of messages. In the current blog, they describe how they scaled it further to trillions of messages. So, this is going to be an interesting read. We designed our search infrastructure to be performant, cost effective, scalable, and easy to operate. We chose to use Elasticsearch with Discord messages sharded over indices, the logical namespace for Elasticsearch messages, on two Elasticsearch clusters. Messages were sharded either by Discord server, which we'll refer to as guild from here on out, or direct messages, DM. This allowed us to store all a guild's messages together for fast querying and running small, more manageable clusters. Since not everyone uses search, messages were lazily indexed into Discord, and we built a message queue that allowed workers to pull chunks of messages for indexing to leverage Elasticsearch's bulk indexing capabilities. But as Discord grew, our search infrastructure began to exhibit a few cracks. Our Redis message indexing queue would drop messages. We used Redis to back our real-time message indexing queue, which held up great at first. However, when our indexing queue got backed up for any reason, which happened often on Elasticsearch node failure, the Redis cluster became a source of failure that began dropping messages when CPU maxed out with too many messages in the queue. Our bulk indexing was fault intolerant on Elasticsearch index or node failure. Part of the reason our indexing queue was so impacted by Elasticsearch node failure is because of how we optimized our bulk message indexing. The real-time index workers pulled batches of messages off the queue to index into Elasticsearch. However, these messages all belong to different indices and Elasticsearch nodes in our cluster. One bulk index operation with a batch of 50 messages might then fan out to 50 Elasticsearch nodes in the cluster. If one operation in the batch fails, then the entire bulk index operation would be considered failed, or re-enqueuing all the messages to be retried. To put it into perspective, let's say Elasticsearch cluster had 100 nodes and we were indexing batches of 50 messages. If one node fails, assuming an equal distribution, and the odds of given batch having at least one message go to that failed node are about 40%. This means that a single node failure leads to 40% of our bulk index operations failing. Large Elasticsearch clusters had large overhead, impacting performance and operability. As our message volume grew, we scaled up our Elasticsearch clusters by adding additional nodes. This allowed us to horizontally scale quite easily by adding more indices and nodes to serve more Discord servers and their messages. However, adding these also meant that each of our bulk index operations were now also spread across a much larger number of indices and nodes. Operations fanned out more, causing slowdown of our indexing performance. Additionally, the more nodes we have in a cluster, the more likely a cluster was to fail at any point. No good path to software upgrades or rolling restarts. Given the system's lack of resilience to single node unavailability, we didn't have a good solution for performing rolling restarts and doing software upgrades. Our cluster had also grown really large and unwieldy with over 200 nodes and terabytes of data total. Any strategy to gracefully drain nodes before restart to ensure service availability would have taken prohibitively long time. We were forced to keep our clusters running, the legacy OS versions and Elasticsearch versions missing both critical updates and performance improvements. Most notably, patching the Log4j vulnerability by disabling JNDI lookups and setting log4j.format message no lookups to true required taking our search system fully offline for a maintenance period while we restarted every Elastic node with a new configuration. Indices with large guilds grew too large. Over time, some of our Elasticsearch indices house the data for some very large Discord guilds. Naturally, large guilds post a lot of messages, causing the indices to grow very large. Each of our Elasticsearch indices in a single Lucene index under the hood, and Lucene has a max doc limit of about 2 billion messages per index. As we learned the hard way, once you hit this limit, all indexing operations will fail. When this happened, our only path to recover was to work with our safety team to try and find the guilds that were solely intended to spam as many messages as possible and delete them. This worked for the time being, but we knew that we would eventually have to support search on the legitimate communities that had posted more than 2 billion messages. The solutions. While our search infrastructure had served its purpose for many years, we began to experience more and more incidents as our cluster failed to handle increased message throughput and query volume. Given our brittleness to rolling restarts and software upgrades, our outdated software also needed an upgrade. Since this was going to be a big undertaking, we might as well take the opportunity to learn and evolve from our existing infrastructure. Deploy Elasticsearch on Kubernetes. By now, Discord was deploying many of our stateless services on Kubernetes. This was a significant improvement to our ease of operability and allowing us to optimize costs with more granular compute and memory resources. We didn't run any stateful services on Kubernetes, but the Elastic Kubernetes operator seemed like a promising solution for orchestrating and managing an Elasticsearch cluster deployed on Kubernetes. With the Elasticsearch operator, we would easily be able to define our cluster topology and configuration and deploy the Elasticsearch cluster onto our Kubernetes node pool. OS upgrades would happen automatically, and the ECK operator exposes ergonomic tools for safely performing rolling restarts and upgrades. Multi-cluster cell architecture to run smaller Elasticsearch clusters. Now that we had committed to running on Kubernetes and using ECK operator, we envisioned a more expensive architecture where we ran a large number of smaller Elasticsearch clusters. In our legacy system, our clusters had grown to more than 200 nodes per cluster. This meant that a given node in the cluster could fail often, and the coordination overhead for the cluster itself was very high. Cluster states of an Elasticsearch cluster don't scale. As a cluster grows to contain more nodes and more indices, the overhead of the cluster's master node also increases. We begin to see that our cluster's master node frequently which would cause indexing failures and growing backlog of messages that fail to index into Elasticsearch degraded every performance and frequent timeouts. In our new search infrastructure, we would create more Elasticsearch indices to remedy this, so each index could stay within the recommendation of 200 million messages and 50 GB of data. These indices would be housed over many more smaller clusters, helping keep our cluster state and coordination overhead down for better performance. We introduced the concept of the logical cell of multiple Elasticsearch clusters, allowing us to have a higher level grouping of a set of smaller Elasticsearch clusters. We'll discuss our usage of cells, how this unlocked new search features and ability to handle large guilds later in this blog post. Within each of these smaller Elasticsearch clusters in a cell, we run dedicated ingest nodes, master eligible nodes, and data nodes. Having these dedicated node roles ensure that master eligible nodes always have sufficient resources to perform cluster coordination. Ingest nodes perform pre-processing and routing can be done as a stateless deployment since they have their own data and can scale up and down to handle volume spikes. Data nodes can be given sufficient heap resources to handle indexing and query operations. Given the different resource requirement for our different node roles, their respective pods are scheduled onto different machine types and node pools. We design each cluster to be resilient to zonal failure with the following: 3 masternode eligible node, 1 per zone, at least 3 ingest nodes, 1 per zone, data nodes. The primary and replica of an index are in different zones with shard allocation awareness and forced awareness balances indices across all zones. PubSub message queue. We migrated our indexing message queue from Redis to PubSub, which allowed us to have guaranteed message delivery and tolerated large backlog of messages. This meant that Elasticsearch failure now could lead to a slowdown in indexing, but we would no longer drop messages. Phew. In fact, the convenience of PubSub's guaranteed message delivery led us to adopt PubSub for other use cases across Discord like task scheduling, but that's a blog post for another day. Batch messages by cluster and index before bulk indexing. We still want to index messages in bulk performance, but our workers should be intelligent and collect the index batches of messages housed on the same cluster. This ensures that each bulk index operation talks to a single Elasticsearch index and node. So if a node does fail, it only impacts the index operations for messages on that node. This is more important now that we have a large number of clusters and indices. To improve our bulk indexing strategies, we implemented a PubSub message router that streams messages from PubSub and collects the badges of messages grouped by their destination, or in our case, the Elasticsearch index and index messages is mapped to. The message router creates a channel and spawns a Tokio task for each destination in the messages being pulled. The router then sends the messages to the task, collects chunks of messages for indexing, which is received on its channels. A router streams the messages from PubSub and extracts a destination or key for each message.in, our case, and the destination in the Elasticsearch cluster and index this message will live on. When the router encounters a message with a new destination, it spawns an unbounded channel and a Tokio task that receives messages on that channel. As the router continues to receive messages, it forwards them on to the appropriate channel keyed by destination. Each destination task collects chunks of messages, now all keyed by the same destination, and the bulk indexes to Elasticsearch. They have put in a code snippet that shows how the message router works. Message router routes messages to a set of dynamically spawned destination. This is a simplified representation of message router used to index. So, this is just a pseudocode, a representation of what really they might have. Okay. Supporting new search use cases. Defining cells of Elasticsearch clusters gave a useful abstraction that allowed us to index messages in different dimensions. The ability to search across all your DMs had long been a requested feature, but one that we were unable to support since all messages were sharded and indexed by guild or DM. Fanning out a search query over all of the user's DMs would be far too expensive. In order to efficiently search all the DMs, we would be able to sort the messages by user rather than by channel, storing all of the user's DMs together on a given Elasticsearch index. This would also mean that we'd store twice as much data, as each message in the DM would be indexed at recipient A's index and recipient B's index. Given that we already planning to reindex all Discord messages as part of our migration to this new architecture, this provided a rare chance to shard and index some messages differently. Guild messages are still sharded by guild ID, but now user DM messages are now sharded by user ID and indexed in separate user DM messages, Elasticsearch cell. This is what powers the new cross DM search functionality now available on mobile. Now, all DM messages and search queries are served by the user DM messages Elasticsearch cell, and the guild messages and queries served by guild messages cell. You won't need to remember who sent you that one message 6 years ago. Give big freaking guilds dedicated Elasticsearch clusters with multiple shards. Add guilds on Discord grew larger with longer histories. More and more of them bump up against Lucine's max stock limit of 2 billion messages. We needed a solution to scale search for these special cases, which we called BFGs, or big freaking guilds. We wanted to retain the performance gains from storing all the messages for a given guild on same Elasticsearch shard, since that still works for the vast majority of guilds, but we needed a solution to scale search for BFGs as well. Elasticsearch indices that have many primary shards, with each shard living on the node in a cluster having multiple primary shards, means data for an index will be spread across multiple nodes in a cluster backed by multiple underlying Lucene indices. To optimize query performance, we normally create an Elasticsearch indices with a single primary shard. This guarantees that all the messages in the index are co-located on a single Elasticsearch node, so there's no fan out and the coordination overhead at query time. For almost all Discord guilds, this result is far more performance search queries, since each query only talks to a single Elasticsearch node. In case of BFGs, however, we are dealing with BF indices and large message volume, billions of messages on a single guild. Having more shards in an index can speed up the search queries, but only when the cost of coordination does not exceed the cost of querying the index. For BFGs, we can realize query performance gains from the parallelism we gain by fanning out a search query to multiple shards, and the coordination cost is worth it. Indexing BFG messages onto indices with multiple primary shards let us scale our search functionality to guilds with many billion of messages and allows for more performant queries for these special case guilds. It also improves query performance for other Discord guilds that previously would have had their resources hogged by the expensive queries to BFGs on the same index. We built a new system that allows us to re-index a BFG's message onto a new index with more primary shards, increasing the maximum number of messages. Importantly, we need to continue to index new messages and serve queries while this migration is happening. The BFG re-indexing flow goes as follows. Number 1, we identify a BFG, a guild where a number of messages is approaching the Lucene max stocks. This guild is currently indexed to index A. Number 2, we create a new BFG index in our Elasticsearch cell dedicated to BFGs within 2x primary shard count of the previous index. Number 3, new messages are now dual indexed to index A and new BFG index. Number 4, we kick off a job to historically index all the guild's messages into new BFG index. Ongoing search queries are still served from index A. Number 5. When the historic indexing is complete, we switch new query traffic from index A to new BFG index. Number 6. Once we are confident that new BFG index is performant and reliable, we stop indexing new incoming messages to index A and kick off a cleanup job to remove all the BFG's messages from too small index. By running a dedicated Elasticsearch cells for BFGs, we can keep the cluster and index configurations standard for most guilds and resources while retaining the ability to adjust as needed for these outlier, more important BFGs. So, how are things going? Now, with our new search infrastructure, we index trillions of messages with double the index throughput for our legacy search, improved median query latency from 500 milliseconds to less than 100 milliseconds, and P99 from 1 second to less than 500 milliseconds. Run 40 Elasticsearch clusters with thousands of indices. Perform cluster upgrades and rolling restarts automatically with no service impact. We're excited to keep powering fast and efficient search for Discord guilds, even as our community grow to each have billions of messages and beyond.